All right, so we are in the blizzard of 2026, and I'm narrating this PowerPoint for my students in New York. I may not leave this on YouTube for that long of a time because I did not write this PowerPoint. As you can see, it comes from Alan Agresti's wonderful stats book called The Art and Science of Learning from Data. And Alan Agresti is an expert in the field of categorical data, a statistician's statistician, if you will. So this will probably be very good. So we are going to start with categorical response comparing two proportions. And when you see the word proportion, if this word confounds you at all, just think of percentages. Percentages are proportions, only with percentages the denominator is 100. And when a statistician uses the term proportion, the denominator is 1. And so think decimals, like don't think 50%, think 0.5. The proportion, 1/2, would be 0.5. So we are going to start with bivariate analyses, a response variable and a binary explanatory variable. The most simple binary explanatory variable is a yes-no variable. These are called indicator variables, but sometimes it's not yes-no. Sometimes it might be drug placebo, or it might be case, people who got a certain disease, control, people who may have tested positive for the disease but didn't actually get the disease, right? So an analysis that looks at any type of a relationship between two variables is called a bivariate analysis. There are two variables. The response variable is one on which comparisons are made. So the explanatory variable defines the two groups being compared. And obviously we'll use statistical methods because this is a stats book. Now, you've dealt with independent and dependent variables in experimental studies, but the terms are also used in samples. You've encountered dependent samples already when you did the paired t-test in your Stats 1 class. There you have an X and a Y, or a pre and a post, and typically you'll subtract the post value from the pre value, and you'll get a difference. And you've already done dependent samples. The paired t-test, it's just a t-test. That's all. So most comparisons of groups use independent samples from the groups. The observations in one sample are independent of those in the other. And that's where you will use random sampling. Example, randomized experiments that randomly allocate subjects to two treatments, such as being randomly assigned to receive either the drug or the placebo. Example, an observational study that separates subjects into groups according to their value for an explanatory variable. That could be your case control study, where cases of subjects, cases are people who have a certain disease, they may test positive and have the disease of interest, but controls, the other group, they might also test positive for the disease, but they don't get the symptoms that could make them have to go to, say, the hospital fighting for their life. So you might want to compare cases with the disease against controls who test positive but don't end up fighting for their life in an intensive care unit with the disease. Dependent samples we already talked about, the paired t-test. The example Agresti is giving is a set of married couples, the men being in one sample and the women being in the other. Disclaimer, I did not write this PowerPoint. This PowerPoint comes from Pearson. So if you find this to be heteronormative and patriarchal, don't complain to me. Complain to Pearson, but they're the educational leader of the world. So, yeah. Disclaimer over. Data from dependent samples need different statistical methods than data from independent samples. Like the paired t-test, it's just a t-test on differences. It's a one-sample test, right? Don't forget that. The paired t-test is a one-sample test of differences, right? It's simple. All right, so now we're going to look at independent sample tests of proportions. So I want to go right to this. This is the population proportion from the first group. This is the population proportion from the second group, and we're taking the difference. Now, this is estimated by the difference of the sample proportions. Now, this is a mistake. I'm surprised Pearson let this thing through. I'm sure Alan Agresti didn't make this PowerPoint. You know, he's probably one of the busiest statisticians on the planet consulting, you know, when other statisticians are stuck. So I'm sure he didn't make this PowerPoint. But these are supposed to be hats. Right, the caret symbol. They're not supposed to be these little rectangles. This is what happens when you use PowerPoint instead of a good program like Canva. You know, Canva doesn't have an equation editor built into it, but, and I'm not getting sponsored by Canva, and I'm not short selling Microsoft. So, yeah, but these are supposed to be hats, right? So this is a mistake. So in your brain, these are hats, not rectangles. But PowerPoint, what are you going to do? All right, so let's look at an example. Aspirin, the wonder drug. Aspirin is a pharmaceutical substance that actually comes from the bark of the white willow tree. It started out as herbal medicine, but then it was purified using modern pharmacology. Better living through chemistry, you know? Experiment. Results of a recent meta, very important word, meta-analysis. This has nothing to do with Facebook. Combined the results of 8 related studies with a minimum duration treatment of 4 years to determine the effects of aspirin on the risk of cancer death. Now, the meta-analysis is an important idea. A meta-analysis is where we combine the results of many different studies, 8 in this case, and it's very sophisticated. A meta-analysis is not something that, you know, the typical college student can do. It requires very sophisticated statistical expertise. So doing a meta-analysis is tough, but reading a meta-analysis is pretty easy. You have your confidence intervals, you have your p-values, you have a few other things that are unique to meta-analyses, but nothing is rocket science to read. So all experimental trials used were randomized and double-blind. This is very good. Hopefully they were placebo-controlled, though I didn't look at these studies. Of the 25,570 individuals studied, 347 of those in the control group died of cancer, whereas 327 in the aspirin treatment group died of cancer within 20 years following the study. So that's long, 20 years. So minimum duration was 4 years. 20 years is long. But with these survival analysis type things, it's, 5-year survival is very common. 10-year survival is very common. These are expensive, time-consuming studies. So here we have the results displayed in a contingency table, and we have deaths, yes, no. So this yes, no thing, right? So we're comparing two proportions, right? We're comparing the death rate or death proportion given placebo administration compared to the death rate or the death proportion given aspirin administration. And so when you divide this by this, you're going to get a proportion. And when you divide this by this, you're going to get a proportion. And it's your choice what you call P1 or P2. Let's see how he does it. So group 1, subjects who took a placebo, and group 2 were the subjects who took the aspirin. Okay, so the first group will be the placebo group. We'll then estimate the difference by dividing those fractions and subtracting the decimals. And so here we're dividing the fractions and we get decimals. And here we're dividing the fractions and we get decimals. And this is the sample size in the first group. This is the sample size in the second group. Now, interesting with this PowerPoint, you got the hat. You don't have the rectangles. So the first slide, which was an error, was missed by quality control at Pearson, or whoever was in charge of quality control for this major textbook. But this slide is correct. These are hats. These are what you're supposed to have. Okay, so we have this difference, 0.007. If we were to move the decimal point 2 places to the right, we would get 0.7%. Doesn't seem like a tremendous percentage, but if you're talking about a lot of people, well, that could be reasonable to consider if you have like a lot of people. I would have used the word more than higher. I would have used more rather than higher. And the reason is higher is usually used in a ratio, which is a multiplicative scale. And when you learn the odds ratio and the relative risk, you'll use times higher. When you look at difference in proportions, more or less is actually a better word. Now, dollars to donuts, Alan Agresti himself didn't look at this PowerPoint. He's a super busy statistical consultant. But I think if you were to ask Alan Agresti, what would the better word be, more or higher? And if you heard me mention relative risk or odds ratio, and I said times higher is used for relative risk and odds ratio, and more is the additive scale of a difference, I think he'd have to agree. But Alan Agresti is never going to watch this video because he's super busy and he's on a very high level. He's an expert. So in percentage terms, the difference was 0.7% less. For the combined studies, the percentage of cancer deaths in the placebo group was 0.7 percentage points. Again, I would really rather use the word more or above than in the aspirin group. I wish Agresti could weigh in on this. Who's right? The guy who wrote, the person. Who's right? The person who wrote up this PowerPoint or me. No one's going to adjudicate this PowerPoint. Example, aspirin, the wonder drug, continued. To make an inference about the difference of population proportions, we need to learn how much the difference between the sample proportions would tend to, now here's an important word, vary from study to study. This is described by the standard error of the sampling distribution for the difference between the sample proportions. All we're talking about when we talk about the standard error of the difference in the proportions is the standard deviation, the estimated standard deviation of this estimator. This estimator estimates this population difference. So this whole difference is an estimated difference in two proportions. And this will be hypothesized under the null hypothesis, probably hypothesized to be 0, but we'll see. So this is described by the standard error of the sampling distribution for the difference between the sample proportions. Okay, so let's cut to the chase. This is the formula. Now, if you remember the binomial distribution, this would be the variance from the binomial distribution when you divide by n and you get a proportion, a sample proportion. This would be the variance of the first sample proportion, and this would be the variance of the second sample proportion. And we are actually subtracting these two sample proportions. And the typical question I get from students is this a mistake? If I write it, whether it comes from Pearson or whether I write it on the board, they see the negative, the minus sign here, and the plus sign here. And I usually get hands saying, is this a mistake? And it's not a mistake. The variance of a difference of independent estimators is the sum of the variance. So these variances actually add up, even though this is a difference. And your Stats 1 professor may have shown you this when they were going over mean and variance. And so this is the variance of P1 hat minus P2 hat, and you take the square root of this whole thing, and that gives you the standard error of this estimator. And the question I sometimes get is, what's the difference between standard deviation and standard error? And they say, there's no difference. I don't know. I don't know why we use two words, because they can be interchanged. But historically, when you're talking about estimators, the standard deviation of an estimator is typically called the standard error of the estimator. And this is an estimator. We're estimating a difference in proportions. So most statisticians will probably call it a standard error rather than a standard deviation, but this is not a mistake on the PowerPoint. So I just want to let you know this PowerPoint slide is perfect. No mistakes. So this is just a reiteration of what we had in the last slide, but it's nice and big. And notice you don't have those weird little rectangles, so this is nice. Looks really good, actually. Yeah, PowerPoint can sometimes look really good. All right, so this is the formula for the confidence interval that you saw in Stats 1, perhaps with a less sophisticated estimator. You always have, well, under asymptotic normality, you always have estimator, plus or minus, and this is called a critical value. And this is your z sub alpha over 2. It surprises me a little bit that it's just a z and it doesn't say z sub alpha over 2, because this is a critical value. And we'll illustrate this probably with a 95% confidence interval. And if you remember from Stats 1, a 95% confidence interval is associated with an alpha value of 5%. And alpha over 2 would be 5% divided by 2, which would be 2.5%. And if you look up that critical value, you'll find the familiar 1.96 from your college Stats 1 class. Okay, so this is a formula. We're really going to just plug it in, and let's do this. Oh, so here's the 1.96 that I told you about, right? And so we're just plugging it in, right? So we plug these numbers in, and this is the difference we got a few slides ago, plus or minus. This is the critical value. This is z sub 0.025, straight out of your Stats 1 class. And this is your standard error that we calculated by taking the square root of that whole thing a couple of slides ago. And what do we get? We get a lower bound of 0.003 and an upper bound of 0.011. Now, put on your Stats 1 hat. Go back to the days of your Stats 1 class and ask yourself, what's important about this confidence interval? What do you care about? If you were working for a hedge fund and this was a clinical trial for a new drug and you had a biopharmaceutical stock that was like a penny stock, and a good clinical trial result could turn this from a penny stock into a dollar stock. And you were an intern working for the hedge fund company, and you saw this. What does your mind think? What do you think when you see this lower bound of 0.003? Give yourself a minute. Think about it. Well, I'll tell you. Both bounds are greater than 0. See, under the null hypothesis of no difference, we would hypothesize P1 minus P2 to be 0. No difference. 0 difference. But when we account for sampling variability and we stick it into our asymptotic normal formula for the confidence interval, both bounds are greater than the hypothesized value of 0. This confidence interval fails to cover the hypothesized value of 0, telling us to reject our null hypothesis of no difference. Let's see, I might have given it away. Let's see how the Pearson team rolls through this. So the inference at the 95% confidence level is that the difference in the two proportions is between these values. Okay. This means that in experiments like this, the population proportion of cancer deaths given placebo would be between 0.003 more, and 0.011 more than the population proportion of cancer deaths taking aspirin. Okay, the point is, both of those numbers, they're more than zero. Since both endpoints, I call them confidence bounds. They're sometimes called confidence limits, but they can be called endpoints as well. And I apologize for the field of statistics having so many synonyms. But since both endpoints or bounds of the confidence interval are positive, greater than zero, we infer that now this is the true difference, right? We inference, statistical inference, a conclusion obtained from inductive reasoning that has the capacity for being wrong. We infer that this population difference is positive at the 5% significance level. See, if you're using a 95% confidence interval, your inference is at the 5% significance level. Conclusion: the population proportion of cancer deaths is more when subjects take the placebo than when they take the aspirin. The population difference is small, but even though it is a small difference, it may be important in public health terms if you're dealing with a lot of people. Small differences when you're dealing with a lot of people can be meaningful differences. When you look at it on the individual level, you got to have some intelligence in interpreting those results. For example, a decrease, this is 1% over a 20-year period in the proportion of people dying from cancer, would mean 2 million fewer people dying from cancer. So that's the idea. If you're dealing with a lot of people, a small difference can be meaningful, you know? So the public health practitioner, epidemiologists being examples of public health practitioners, they must look at it through the lens of the public, which is many people. Your own personal physician may look at it through the lens of one person, and that would be you. So this is a complicated subject that a Stats 2 class is really just, we're venturing into the very tip of the iceberg here, you know? So let's look at some Minitab output. Minitab is a statistical package that's used in education a lot. I use SAS. It's free for students and educators, and I don't know if you can put Minitab on a resume, you know. SAS on a resume? Yeah, that's something you can talk about in a job interview. Minitab? I don't know. Yeah. But anyway, I guess what's important here is in the real world, well, this is a relatively simple calculation. This is something you could do on something like Microsoft Excel, though I wouldn't recommend it because you can unknowingly make an error on Microsoft Excel very easily and think it's not an error. But when you use a dedicated statistics package like SAS, for example, that program's not going to run unless most likely you got it right. You can still make errors, but SAS is designed to really make you think very carefully about what you're inputting, lest an error be made. So here you have this. Now, notice here they are called bounds, like I did. I called it the lower bound and the upper bound. And That's what this is used in Minitab. And the confidence level is 1 minus the significance level, or, well, in this case, 100% minus the significance level as a percentage. So that's that. So the benefit was consistent across the different trial populations from the different randomized studies, suggesting the findings have broader scope of generalization. Generalization is the ability to use a single set of studies in populations that may not necessarily be super broad, and being able to generalize these to other populations. So the concept of generalizability, and if you're studying psychology, this is called external validity. So my audience has people going into business and medicine and psychology. So generalizability and external validity, they mean the same thing. So before concluding that aspirin benefits a larger population, it is important to replicate the study to see if results are similar or different for populations used in this study and other populations. Unfortunately, when tenure is decided in research institutions, replication studies are not weighted as heavily as novel studies. And some people would consider this weighting a threat to honest and ethical science. I leave that for your own consideration. Summary: interpreting a confidence interval for a difference of proportions. So, as I mentioned, you are going to want to look to see if the confidence interval captures the hypothesized difference in proportions. Now, the reason why this PowerPoint slide uses the 0 over here is because under the null hypothesis, we are hypothesizing no difference in the population proportions. No difference is a 0 difference. So that's why this PowerPoint bullet point has the 0 over here. If all the values in the confidence interval for the difference in proportions are positive, you can infer for the first proportion minus the second proportion greater than 0. Or P1 is greater than P2, because if the first proportion is greater than the second, the difference will be positive, greater than 0. If all the values in the confidence interval, now, what you really do is you look at the endpoints, but this is absolutely correct, but you look at the endpoints, or what are also called the bounds. If all the values in the confidence interval, or both bounds, are negative, you can infer that the population difference with the first proportion minus the second proportion is, in fact, negative. Or P1 is less than P2, because if the first proportion is less than the second population proportion, then this difference will be negative, less than 0. Now, the magnitude of the values in the confidence interval tells how large any true differences is. Don't forget, the confidence interval estimates, that's the word, estimates the true difference in proportions. It's just an estimate, but it's an estimate that incorporates the standard error of the difference in the sample proportions. If all the values in the confidence interval are near zero. Now, what this author means is if the bounds of the confidence interval capture the hypothesized difference in proportions of zero difference, that means no difference, then the true difference may be relatively small in practical terms. Okay, next slide. Summary. Two-sided significance tests for comparing two population proportions. And when you see the phrase two-sided, it is the same as two-tailed. Some books, some practitioners prefer to use two-tailed. Others prefer to use the term two-sided. It doesn't matter. Assumptions. Categorical response variable for two groups. Yes, no. Independent random samples, either from random sampling or from a randomized experiment. Now, don't forget, a randomized experiment is different than a random experiment. A randomized experiment means the study participants or subjects are randomly assigned into the different treatment groups. For example, a placebo group and a DRUG group, for example. The sample size in the first group and the sample size in the second group has to be large enough for that beautiful asymptotic normality, which is where we got that critical value of 1.96 from. That's because this test on proportions has to use the Z distribution. That's asymptotic normality. And we need at least 5 successes or yeses and 5 failures, nos, in each group if using a two-sided alternative. And the same is true for the confidence interval. Summary. Two-sided significance tests for comparing two population proportions. Hypotheses. I already mentioned this, but it is worth repeating. Under the null hypothesis, there's no difference, zero difference in the true population proportions. Zero difference is mathematically equivalent to the first true population proportion being equal to the second true population proportion. Basic math. The alternative hypothesis is the hypothesis of interest to the investigator. That is not necessarily true. It depends who you're working for. If you're working for the nuclear power plant or the data center, it is the null hypothesis of no difference in some adverse event that you're going to want the results to provide evidence in favor of. So this is a mistake very often. There's no way Alan Agresti wrote this PowerPoint. Most likely he had a graduate student write this. And I'd say to the graduate student, are you working for the nuclear power plant or the data center, or are you working to show efficacy in a pharmaceutical preparation? If you're working for the data center or the nuclear power plant, you're rooting for the null hypothesis that there's no difference in adverse safety events. But if you're working for a pharmaceutical company and you're trying to demonstrate efficacy, then you're rooting for the alternative hypothesis. I see a lot of community college professors make this same mistake. There's no way Alan Agresti made this PowerPoint. He's too good, So this is a little mistake. Sorry, but it is. So we have two-sided alternative hypotheses, and we have one-sided alternative hypotheses. We could show that one proportion of yeses is better than the second proportion, or we might want to demonstrate that one proportion of successes is lower than another proportion. It all depends on the specific research, and this is just a general formulation. So we have this nice little test statistic. Now, when you see -0, this implicitly tells us that the null hypothesis is that there's no difference, zero difference, which is relatively standard and the most common application. But it doesn't have to be. We could make this 0.3 if there was a defensible reason for doing that. And often there is, but most of the time we use 0. And this subscript 0 means we're calculating the standard error of the difference in proportions, difference in estimated proportions. But we're calculating the standard error assuming that the null hypothesis is true. Now, again, this z distribution means we are modeling the null distribution using asymptotic normality. So that's an important idea to understand. We need a reasonably large sample size in order to do it. Here we factored out this term. This comes straight from factoring. And this minus sign is correct. This is correct. Notice we actually do have the hat symbols. We don't have those weird little rectangles as artifacts in the PowerPoint. So this is true. This is a good slide. Summary: two-sided significance tests for comparing two population proportions. So the p-value is calculated the same way as if it was a one-sample test. We have tail probabilities, and if it's a right-tailed test, we use the right tail probability. If it's a left-tailed test, we use the left-tail probability. And if it's a two-tailed test, you double the smallest probability. So it's really the same exact thing, no difference, right? So conclusion, smaller p-values give stronger evidence against the null hypothesis, supporting the alternative hypothesis. Interpreting the p-value in context. If a decision is needed, we reject the null hypothesis if the p-value is less than or equal to the significance level. And this 0.05 is the 5% significance level. And this is the de facto significance level on planet Earth in almost any laboratory that you will find on our planet, in any country, in any municipality, in any village. The 5% significance level is the de facto significance level. And there was a really important reason for this. You see, in the 1930s, a statistician named Ronald Almer Fisher, and he's usually just called R.A. Fisher for short. Most people don't even know his middle name. But R.A. Fisher said in the 1930s in a book, he wrote, 1 out of 20 seems like a good number for the type 1 error probability. Now, 1 out of 20 is 5%. And Homo sapiens love rules. So since Homo sapiens love rules so much, that 5% stuck. Yet it was a very glib, flippant, arbitrary value that in his writing, he wanted to show that, well, if you need to use something, 5% is a good starting place. And yet somehow that 5% stuck. But I don't think that was Fisher's intention for it to stick the way it has. But again, Homo sapiens just love rules. All right, so let's do another example. TV watching and aggressive behavior. If you've studied psychology and you know the work of Bandura and Walters, this is something that might be super familiar to psychology majors. A study considered whether greater levels of television watching by teenagers were associated with a greater likelihood of aggressive behavior. Researchers randomly sampled. That's good. Random sampling means, the asymptotic normality. As long as we have a decent sample size, we can use that, asymptotic normality, that Z critical value that we look up. 707 families in 2 counties in New York State and made follow-up observations over 17 years. This seems like a pretty expensive study for psychology. But I don't, hey, good deal for us. So let's look at this table too. So you're always in this difference of 2 proportions. You have the yes, no, right? Aggressive act, yes, no. And we have TV watching, less than 1 hour per day, at least 1 hour per day. And I would assume it's TV watching with violent content. If you're watching Blue's Clues or Paw Patrol, I don't think this would count. Paw Patrol, Paw Patrol. So anyway, let's go into this. So define group 1 as those who watched less than 1 hour of TV per day on the average as teenagers. Define group 2 as those who averaged at least 1 hour of television per day as teenagers. So piece of 1 is the true population proportion. Population and true can be used interchangeably. The true proportion or the population proportion. It means the same thing. Committing aggressive acts for the lower level of TV watching. And of course, in the study, you'll have to define what an aggressive act is. And in medicine, this is called the case definition. P2 is the same exact thing for the higher level of TV watching. So we are going to assume that you wouldn't do the study unless you had an a priori assumption that P2 was going to be greater than P1. I mean, no one in their right mind would think that watching violent TV would be, somehow calming or, associated with lower acts of aggression. So I think the alternative hypothesis is pretty clear in this one. Okay, so the null hypothesis is that the difference in the population proportions, the difference in the true proportions, is 0. In other words, these proportions are equal against the... Now, okay, so this guy is using a 2-sided alternative, considering the possibility that watching violent TV could make somehow less prone to, be aggressive. I mean, there's nothing statistically wrong with that, I guess, but it seems like, a little weird. But statistically, you could say 2-sided tests are more robust. This is what a statistician would say. If the statistician who wrote that slide heard me say that and they wanted to defend themselves against what I said, said statistician would say, yeah, but there's greater robustness in departures from the assumptions, namely asymptotic normality, if you have a 2-tailed test. So, that's what the statistician could say. Okay, now here we have that PowerPoint artifact again. I don't think Pearson reviewed this slide because this rectangle should be a hat. So quality control let one slip by. All right, so we got we got P, not rectangle, but P hat is 0.225, which is about 22.5%. Decimal point, 2 places to the right. All right, so this is what's called our estimated proportion or our sample proportion, right? Okay. So, another PowerPoint slipped through quality control. Okay, so we got the standard error. So this is called pooling, Pooling. So let's get the 5 plus the 154. Let me show you where this came from. See the 5 plus 154? See how we're pooling it from both groups? We have the low TV exposure group, and we have the not low TV exposure group. And we got the 5 and the 154, and we're pooling them together, right? So this is a pooled population proportion, just like the pooled variance t-test that you learned in Stats 1, right? We're pooling that. And so this really shouldn't be here. If anything, there could be a little p under the p for pooling. So this is a PowerPoint artifact that escaped quality control. Surprising, because Pearson is like the educational leader, in the educational space. They're like the corporate education leader of the world, But it shows not every quality control process catches every problem, just like no medical test. If you get a positive result from a medical test, it can be a false positive. And if you get a negative result from a medical test, it could be a false negative. Not all tests have 100% accuracy. Not all quality control departments will pick out every PowerPoint mistake, So it's a beautiful thing that this is here, because this mistake is perfect in a statistics class, All right. Ooh, it's more. Oh my God, how did this go through? Okay, well, so here we have, this is the pooled, so we're pooling these estimated proportions, and it's the same exact formula, we had before. And this is just the standard error of the difference in proportions. These should be hats. I did not make this. This is Pearson, but you know what? Here's a good thing, having a human go over this, Having a human go over this, I guess there's still a good reason for me to have a job, Maybe I'm not ready to be replaced by like an AI bot or something. So these should be hats, right? This is the z-score, asymptotic normality, right? Crank out a z, and we interpret this z just like we would in Stats 1. And if you remember from Stats 1, the magnitude, also known as absolute value, the magnitude of this z-score is large. 4. This is a 4 sigma event. This is in the z-score, the magnitude of this z-score is large. I mean, it happens to be very small, but the magnitude is large. So the left tail probability of this thing is minuscule, which means the p-value is going to be minuscule. I mean, you don't have to actually calculate the p-value. It's going to be minuscule. But hopefully there's a little picture of this PowerPoint artist doing it. So it's minuscule. So he's letting this, he, she, they, them, letting this app calculate the p-value. It's double this left tail probability, which would be the area under this curve from, where my mouse is going. And it's so minuscule that you can't even see it. So this is a tiny little p-value. And the app says the p-value is 0.0001. So if you're working for the video game company that has aggressive content, You're not going to be rooting for this alternative hypothesis, and you're not going to like this p-value at all. But if you're working for a public interest research group that doesn't want violent video games or violent TV shows to be broadcast, oh, you're going to love this p-value because it shows that there is a significant association. Okay, so conclusion. Since the p-value is less than 5%, right? 5%, the de facto significance level, because R.A. Fisher said it seemed like a good number and it stuck. We reject the null hypothesis. And that provides evidence that the true population proportions are different, right? And notice the word differ is used, right? Differ, different. The sample values suggest that the population proportion is higher for the TV level of TV watching. Again, it must be violent TV. Like, this can't be from Paw Patrol and Blue's Clues, So, significant difference. Two groups are called statistically significantly different if a test based on comparing the two population parameters result in a significant result, that is, a small p-value. Small on planet Earth is usually less than or equal to 5%, because R.A. Fisher said 1 out of 20 seems like a good number, and Homo sapiens love to follow their rules. So, the standard error for comparing two statistics. Now, this is a little general here, but the standard error of the difference between two estimates. For two estimates from, now this is really important. The word independent is necessary for this, and there's one word that's missing, right? If Alan Agresti saw the PowerPoint that his graduate student made, he would want the word random to be here. For two, and really this word should be estimators, not estimates, if you really want to get technical. So for two estimators from independent random samples, the standard error is, this is not a mistake. You're taking the variance from the first one plus the variance from the second one, because if you have independent random samples, you can add up the variances, and then you take the square root to turn it into a standard deviation. So this slide is 100% correct as long as you stick the word random in here. So in your notes as you're reading this, if you're copying this down, because that's how you learn, just stick the word random in here and you'll be fine. Section 2.1, quantitative response, comparing two means. This is very, very important if you're in a Stats 2 class and you're planning to study analysis of variance, or if you're thinking of going into psychology, because psychology programs love analysis of variance. I mean, if there's one favorite statistical method for psychology programs, it's analysis of variance, followed by confirmatory factor analysis. But you won't get confirmatory factor analysis in a Stats 2 class. It's a beautiful idea. But this is really important for you psychology students out there. So let's do an example here. Example. A graph is worth 1,000 words. Participants randomly split into two groups. One group read a short generic text about the effectiveness of a medication. The other group read the same text but accompanied by a basic bar graph that mirrored the text. Participants rated the perceived effectiveness of the drug on a 9-point scale: 1, not at all, and 9, very effective. Here, we have a table of summary statistics for both groups. Now, you should write that word summary statistics in your notebook, because that's the statistical phrase that represents this statistical table. The summary statistics are the mean, the sample mean, and the sample standard deviation. Now, it doesn't say the word sample, but this here says the word sample. And this tells us that it's a sample mean and a sample standard deviation. The sample size is not considered a statistic, but it has to be presented with your summary statistics so that you can evaluate statistical significance. Now, before I continue, we have to review a little statistics 1. When you see a table of summary statistics, that's the mean and the standard deviation, this tells us about a very important assumption. And I want to ask you, what is the assumption when summary statistics are presented in this way? Time to think. The answer? We are assuming a normal distribution. Why? Because these sample mean and the sample standard deviation are what is known as sufficient statistics. Sufficient statistics. That means that all the information that's in the sample, or I should say both samples, because we're comparing two samples, are in the means and the standard deviations. All the information. So in a sense, under this sufficiency of these two statistics, you could take the raw data and figuratively throw it all in the garbage, paper shredder, and you wouldn't lose any information if you have a normal distribution for both groups. Now, if you didn't have a normal distribution, you wouldn't use the mean and the standard deviation. And I'm going to ask you, from your Stats 1 professor, who's probably spent a lot of time on mean, median, and mode, what would you use if we didn't have evidence that both populations were normally distributed? I'll give you a minute to think. The answer? Instead of mean and standard deviation, you'd use median and interquartile range. But here, this is exactly how you would want to present it if you have evidence of normality. And that can be tested using a goodness of fit test, and the most common is the Shapiro-Wilk test, SHAPIRO-WILK. And you will find that in SAS, the SAS programming language, under the proc univariate procedure. And all you have to do is put the word normal after the word univariate, just one word, and it cranks out the Shapiro-Wilk p-value. And all you have to do is see whether the p-value is less than or equal to the significance level. And you can test normality. So easy using SAS. So easy. Okay. So obviously these must be normally distributed because you're presenting it in this way. And this is all you need, right? All right, let's continue. Oh no, look. Okay, so as a statistician, I have problems with this. I don't like this. I don't know if Alan Agresti would like this. See, you just gave a table that assumes normality, and now you're giving box plots? I have a big problem with this. If you remember from your Stats 1 class, these vertical bars here, these aren't the means. Do you know what they are? They're the medians and the interquartile range. So the data visualization assumes non-normality, because why would you use a box plot if you have normally distributed data? You just give a table the way you did. Now, I'm pretty sure there's no way Alan Agresti made this slide himself. I don't think he would do it. And man, I would love him to react. I would love it if he got a screen capture program and reacted to what I had to say. Alan Agresti, if you're watching this, why would you go from means and standard deviations to medians and interquartile range? I'm confused, but my students won't be confused. I have a problem with this. However, let's look at it anyway. You can see the median rating for the words and the picture is higher than the median rating, the vertical bar, from the text only. If you never took a Stats 1 class and you didn't know anything about variability, you might say, oh, this is higher than this. Ergo, this has to be better than this. In other words, adding the picture has to be better than the text alone. But if you've taken the Stats 1 class, in your mind, you'll already be thinking, yeah, but is it significantly better? I don't care if it's mathematically better. I only care if it's significantly better. And I'm going to use the 5% significance level because on planet Earth, that's the de facto significance level. Why? Because R. A. Fisher in the 1930s said 1 out of 20 seems like a good number. All right, let's continue. All right, example. A graph is worth 1,000 words. Continued. How can we compare the ratings between the group that saw the text and the graph and the group that just saw the text? One way to compare the two groups compares the mean ratings by looking at their difference. And if you're going to look at the difference in means, what is your distributional assumption? That would be normality. Group 1. So this is just a repetition. Group 1 is the text and the picture. Group 2 is just the text. So this is just a repetition of what we had before. Okay. Now we're back to approaching this thing like the underlying populations are normally distributed, because we're back to means and standard deviations. X bar sub 1. Now that's how this is read. This is very important. Let me say this again. We read this symbol as X bar sub 1. We can also read this symbol as the sample mean from the first group. And we can read this symbol as the sample mean from the second group. The subscript tells us the group. And we can take the difference of the two means, and what we get is 0.7. This is the mean difference. Technically, you'd probably rather say the difference in the means, or even more technically, but more verbose, the difference in the sample means. First group minus the second group. That's the most verbose way of saying it, but the most accurate way. We have an estimator. we have another estimator. We're subtracting. We're going to need a standard error. But I'm assuming he's going to do the pooled variance t-test first. So it's complicated. Okay, so I already said this, but in this experiment, the mean rating on the perceived effectiveness of the medication is 0.7 points higher in the group that also saw the graph. This analysis uses descriptive statistics only. So the middle school student can use descriptive statistics. And I know this for a fact because both of my children went through middle school. So, yeah. Okay. Now, the mean and standard deviation of the sampling distribution for the difference of two sample means. Now, this is missing two words over here, but the words are present here. Independent and random. These words must be present for this to be valid. Okay, so this is very important. For two independent random samples of size N1 and N2 from two groups with population means mu, Greek letter mu, like mucus, mu1 and mu2, and population standard deviations, lowercase Greek letter sigma sub 1 and lowercase Greek letter sigma sub 2. Now, these are population standard deviations, not sample standard deviations. And that's why this is called the standard deviation. It's not the sample standard deviation. It's not the standard error. This is the population standard deviation when the underlying standard deviations from each group, group 1 and group 2, are known. And this is correct. This is not a mistake. You do add them, as I mentioned before. Standard error. Now we're going from the concept of standard deviation when the populations are known to the concept of standard error when the standard deviations or variances from each group are unknown but are estimated from the data. In practice, we will have to estimate the standard deviation because it depends on the unknown population standard deviations. Replacing sigma sub 1 and sigma sub 2 by the sample standard deviations, S sub 1 and S sub 2, we get the standard error of the difference of the sample means. And even though this is a minus sign, this has to be a plus sign. So this is a correct slide completely. Now, this confidence interval, even though we don't see a Z over here, we see a T. Just like when we did students' t-test in your Statistics 1 class, when we estimated the population mean with the single sample mean, we have a similar idea here because we are estimating the variability rather than knowing the variability. So this still requires each group to be approximately normally distributed for this critical value to be valid. So this is important. Okay. Confidence interval for the difference between population means continued. For two samples, and really I should emphasize for two independent, random samples with sample sizes n sub 1 and n sub 2 and now it should say sample standard deviations. Put the word sample over here in your notes. And sample standard deviations. Technically, this should be a lowercase s, not an uppercase s. I'm being very technical here. Very, very technical. If Alan Agresti was to watch this, I don't think he'd have anything to say. This is the MLE. If you have the lowercase, it's what we're going to deal with in Stats 1 or Stats 2, which is the unbiased estimator. So this should be a lowercase s1 and a lowercase s2, just to be 100% technical here. A 95% confidence interval for the difference in the population means mu, like mucus, Greek letter, sub 1 minus mu, like mucus, sub 2. Right? So this is the formula here. This is the critical value from students' t-distribution, right? In fact, this is the 97.5th percentile, if you remember, from your Statistics 1 class. Okay. Confidence interval for the difference between population means continued. For two samples with sample sizes n sub 1 and n sub 2 and sample standard deviations, you got to put that word in here in your notes, sample standard deviations, and make these lowercase s's, lowercase s sub 1 and lowercase s sub 2, a 95% confidence interval for the difference in the true population means is, and again, we have the same exact idea, right? Same thing. You have the estimator, which in this case is a difference of sample means, plus or minus a critical value, which comes right from the student's t-distribution, just like you did in Stats 1. And here you get the standard error of this estimator, this whole thing, and this plus sign is correct. Even though this is a minus, this is correct. Software gives us the t sub 0.025, which is the t-score with right tail probability 0.025, which is the 97.5th percentile. So the total probability is 0.95 between these two students' t critical values. This is the 2.5th percentile of students' t distribution. And this is the 97.5th percentile of students' t distribution. Now I'm really hoping there's a picture in the next slide. Please be a picture. Pearson, give us a picture. No picture yet. Well, I already talked about the assumption. So this method assumes a quantitative response variable observed in each of the two groups, obviously. Independent random samples, I already talked about that, from the two groups, either from random sampling or a randomized experiment, already talked about that, and an approximately normal population distribution for each group, already talked about that. This is mainly important for small sample sizes. No, this is important. You got to do the Shapiro-Wilk test. No, this is important. Yeah, I see. Yeah, no. Don't always rely on the central limit theorem. Do the Shapiro-Wilk test. Cover your bases. You know what I mean? And even then, the method is robust to violations of this assumption. That is true. So if there are departures in the assumptions, if you have a two-tailed t-test, it is a very robust test. So that's true. But I would never, I'm making this video in 2026, where you have computer software. Like, this isn't 1975, This is 2026. With SAS, you can run the Shapiro-Wilk test with a couple of lines of code. And you just click, and you get the p-value. Like, why would you not do it? It's easy. Oh, and SAS is free for students and educators as of this video. Why would you want to use anything else? It's the preeminent statistical software program, pretty much on planet Earth, but definitely in the biopharmaceutical space. Definitely. SAS is fantastic. What makes SAS so fantastic is that if you don't know what you're doing, you're going to get an error. See, on Microsoft Excel, you will get a number even if you don't know what you're doing, and you might think that number is right when it's really wrong. On SAS, if you don't know what you're doing, you're going to get an error, which is good because you don't want to be lulled into a false sense of thinking you got the right answer when you don't have it. All right, let's continue. So when using software to analyze the data, a 95% confidence interval for the difference between the mean ratings of the effectiveness of a medication between people who read a short description of the medication accompanied by a graph and people who just read the short description but didn't see the graph. And this is our confidence interval. The lower bound, this is called the lower bound. It could also be called the lower confidence limit. This lower bound, notice, well, what would you, so let me give you some time to think. I want this to be as interactive as it's not easy to make a YouTube video interactive, but I'm going to make this interactive. Okay. Here's the lower bound of this confidence interval, right? What do you notice about this? Well, the lower bound is greater than what number? Time to think. Well, what is our null hypothesis? Our null hypothesis is that there's no difference in the means. That means there's zero difference. Zero. Both bounds are greater than zero. That means that there's a statistically significant basis for rejecting the null hypothesis. This even supports a one-tailed alternative hypothesis where the effectiveness of getting the picture and the words is better than getting just the words. So both of these bounds are greater than zero. So when you look at this confidence interval, that's what you see. All right. Is it reasonable to assume an approximate normal population distribution for product effectiveness ratings in the two groups? How does this affect the inference? Well, that's where the Shapiro-Wilk test comes in, That's not the only test in the world for normality. There are more powerful tests than the Shapiro-Wilk test under a variety of alternative hypotheses. But to the best of my knowledge, the Shapiro-Wilk test is the most popular. And, with SAS, you just put the word normal in proc univariate and you get the p-value. Just with the snap of a finger. Oh, so they're not doing it, and okay, they're eyeballing histograms. All right, this is not modern statistical practice. You don't eyeball. Well, I mean, there's nothing wrong with eyeballing histograms as a first pass in the data. It's very good. It's called exploratory data analysis. And eyeballing data visualizations is a great first pass. But at some point, you got to do the Shapiro-Wilk test on both groups. But I know what he's going to say. There's some skewness here. See how there's a lot of mass here and not too much here? Right? There's some right skewness. And see how this one, this is a little left skewed because you have a little more mass on the left side of this histogram. But my guess is that this one might not be that bad. But the fact that it sort of goes into this like drop quickly, this might not be normal. But again, I'm eyeballing it. That's not what you want to do in 2020. I mean, you can do this as a first pass, but you still got to run the test. So let's see what he has to say. So the side-by-side box plots shown earlier indicate a right skew for the text and graph, which is also evident in this little visualization, and a left skew for the text-only group, which is clear in this visualization. However, the shape of the histograms doesn't indicate any dramatic deviation from normality. Now, how would the Stats 1 or the Stats 2 student know that? Well, they wouldn't. And I would never write this in a paper. If someone hired me to do their stats and I wrote this, they'd fire me. You got to do the test. Also, the sample size is large enough for the center. I disagree with this. So in theory, so here's what he's getting at. In theory, if you truly have independent random samples, if that's really the case, then okay, the central limit theorem will hold. But if you're ever asked to critique a scientific paper when you are in your major, in your upper division courses, the most vulnerable point in a paper, most often, not always, but a very good vulnerable target to hit in critiquing a paper is the randomness of the sample. Is it really a random sample? You can look in the methods section, and very often you can find reasons in the real world why you don't have actual random samples. And so going right to the central limit theorem, this bothers me so much. I wonder what Alan Agresti would have to say if I said to the writer of this PowerPoint, do the test, run the Shapiro-Wilk test, come on. But, whatever. That's why. Okay, so this is very important. Alan Agresti calls his book The Art and Science of Learning from Data, 5th edition. There's a reason why Alan Agresti, who's one of the best statisticians in the world, why does he use the word art in a math discipline? Do you see how this is an art? See how I'm like, I wouldn't hang my hat on the central limit theorem because the random sample is the most vulnerable target in critiquing a paper, typically, not always. And your central limit theorem is based on the the independent random samples. Because this is, difference in two means. So you need the independence also. So that's art. See, I'm getting at these nuances. That's why he titled his book the way it is. And I'm a huge fan of Alan Agresti. I doubt highly he wrote this PowerPoint himself, Do the Shapiro-Wilk test. Maybe they will. So let's see what we have here. So the degrees of freedom value for the t-score, ooh, they're the devil's in the details on this one. If you did this in Stats 1, the devil's in the details in this one. But shown in the computer output is 57.5. All right, so let's just say, okay, the computer gave us the right t-score, got the degrees of freedom, and let's see what we get here. So this is assuming normality. This is assuming normality. We got the margin of, this is the difference in the means estimated. And here's the confidence interval. We got the lower bound, we got the upper bound. Now remember from Stats 1, if you have a 95% confidence interval, this corresponds to a two-tailed hypothesis test with the significance level being 5%. Lower bound is greater than 0. Of course, the upper bound has to be greater than the lower bound, so they're both greater than 0. Reject the null hypothesis. Simple, simple, simple. All right. So this is repetition, right? We already read this. I don't feel like writing this thing again. This is repetition, just plugging it in. This is the t critical value. This is the estimated standard error of the difference in the sample means, right? T critical value, standard error, right? And here's how we got the bounds. But the software did this. And at this level, some professors want their students to roll through the pooled variance t-test to give them practice with it so that when they hit analysis of variance, they really understand what they're doing. And other professors say that the number crunching is too much work. By now, you should understand the concepts. I'm on the fence. I'm so on the fence. Should the students have to go through the number crunching in this, or should they just get it from software? I'm actually on the fence. If my students want to give me their opinion, I'll listen. All right. So let's see what the PowerPoint author has to say. We can be 95% confident that the difference in the mean ratings between the people reading the text and seeing the graph and the people just reading the text falls between the lower bound and the upper bound. I don't like the language of this because in the standard, and I'm going to throw a word at you, which you can Google, in the standard frequentist, that's a word, I didn't make that up. The standard frequentist, that's a word in statistics. Interpretation is that this mean difference, which we hypothesize to be 0, it's fixed. It is what it is. We don't know what it is. We don't know the true mean difference. We can hypothesize and say, hypothetically, suppose the mean difference is 0. But basically, this interval, if we were to perform this experiment 1,000,000 times, the width of this interval would vary, the bounds of this interval would vary, but 95% of the time, these bounds would capture whatever the true, which could be synonymously used with the word population, whatever the true mean difference or the difference in the population means, what that difference really is. We hypothesize it to be 0. So I'm not super happy with the way this is worded because when you teach Stats 1 and Stats 2, you typically teach the standard frequentist interpretation of statistical practice. And if you get Bayesian, now you need to, and that's a real word, Bayesian, now you need to talk about priors and posteriors. And so we don't really, well, at least in my institution, oh my God, I could only imagine what my colleagues would the looks they would give me if I said the word Bayesian. So I would like you to imagine this experiment being practiced, replicated is a better word, replicated a million times over and over again. And these bounds will vary and the width of the interval will vary, but 95% of these intervals would capture whatever that true difference in the means is that the human being doesn't know. Because if the human being knew it, why would we spend the money to study it? It would be a moronic waste of time. But hypothetically, suppose it's zero, right? Well, this confidence interval fails to capture this hypothesized value of zero. And so that's really what we're doing here. Now, I'm giving you a lot of very specific details in statistical practice that might require you to really think about this carefully. If you're taking a Stats 1 class, this might be a little above you, but my intended audience is a Statistics 2 class that have already had excellent professors in Statistics 1. Okay, so the next thing we want to do is interpret the confidence interval for the difference in population means. And we did that already. We saw that it failed to capture zero, suggesting a statistically significant difference from zero. And we saw that both bounds were positive. So we already talked about it. So this slide is not worth going over again. It's repetition. A confidence interval for mu sub 1 minus mu sub 2 that contains only negative numbers, in other words, both bounds are less than zero. We then infer that the first group's population mean is smaller than the second group's population mean. Okay. Summary. Two-sided significance test for comparing two population means. 1, assumptions. A quantitative response variable observed in each of the two groups. Good. Independent random samples. I dug into this deeply. Without this, the whole central limit theorem is useless, But again, the whole random sample thing, you got to read the paper really carefully because this is a target area if you ever want to discredit a paper, right? There are, what do you call those, fact checkers. Corporations hire fact checkers to discredit papers that go against, their stakeholders' narratives all the time. And one of the vulnerable targets, are they really random samples? So if you ever want to become a fact checker, this is your vulnerable target. And then you can't really rely on the central limit theorem, Do the Shapiro-Wilk test. You should do it anyway. Approximately normal population distribution for each group. Yeah. This is mainly important for small sample sizes, and even then, the two-sided test is robust to violations of this assumption. Yeah, I guess that's kind of true. Yeah, but still do the Shapiro-Wilk test. Because here's the thing. If you reject the null hypothesis in the Shapiro-Wilk test, if you have something like SAS, with a couple of lines of code, really, a couple of lines of code, you can do the non-parametric alternative, which is called the Wilcoxon rank sum test. And it's called proc n par one way. Couple of lines of code, and you can use your box plots and you can compare the medians instead of the means, and it's the easiest thing in the world. So do it. Just do it, The Shapiro-Wilk test. All right, so the null hypothesis is that there is no difference, zero difference, or no effect. That means the population mean from the first group minus the population mean from the second group is zero because they are equal. Subtracting equals gives us 0. Okay. We have our 3 choices for the null hypothesis: the two-tailed or two-sided, the one-tailed or one-sided, and the one-tailed or one-sided. Better, worse, difference, right? This says there's a difference. This says the first group is better. This alternative hypothesis says the first group is worse. 3 ways to go. It's the researcher's choice which one of these you want to use. But there is one little caveat to this. How do you know which one to pick? Well, in the world that we live in, the real world, where cash is king, in the real world, it depends who's paying your salary, because that tells us whether we are rooting for the null hypothesis or for the alternative hypothesis. And if we are rooting for a one-sided alternative hypothesis and you use a two-sided alternative hypothesis, you have just wasted statistical power. So it depends who's paying your salary. But also, the art and science of learning from data. If I could add one word to Alan Agresti's wonderful book, I would love it to say the ethical art and science of learning from data, because statistics can be misused. And you really have to know statistics well to be able to detect the different ways statistics can be spun. But with Alan Agresti's amazing book, you're on your way, you know? He's top notch. All right. So this test statistic is not the pooled variance t-test. So in case you took stats 1 and you did the pooled variance t-test, you'll notice that this is the sample variance from the first group, and this is the sample variance from the second group. This is not a pooled variance. So this is not the pooled variance t-test that you did in stats 1, which means degrees of freedom. You don't want to do that by hand. You really don't want to do that by hand. I mean, any professor who makes their students do the unequal variance t-test by hand, calculating that degrees of freedom, I don't know. That's where I'm not on the fence. Yeah, I'm not on the fence. I think that's cruel and unusual, if you ask me, but whatever. So software is going to give you the p-value. And really, I'm right. This video really is intended for my Statistics 2 students who missed one of my lectures due to a blizzard, the blizzard of 26. It was a blizzard. And they are going to learn how to use SAS. And that thing just cranks out the p-value. So if you know what a p-value is, this isn't nuclear engineering, this is easy if you know what a p-value is. But from stats 1, unless you didn't have a good stats 1 teacher, of course you know what a p-value is, because if you major in anything, you're going to be reading papers in your major where p-values are presented. So if you have a two-sided or two-tailed significance test, you have a two-tailed p-value. And you're going to double the right or the left tail that you get. So you did this in stats 1. So, it's the same exact idea. Smaller p-values give you stronger evidence against the null hypothesis and in favor of the alternative hypothesis. And interpreting the p-value in context, and if a decision is needed, the p-value decision rule is to reject the null hypothesis if the p-value is less than or equal to the significance level. Again, the de facto significance level on planet Earth is 5% because Ronald Almer Fisher wrote glibly in a famous book that contributed substantially to the field of statistics that 1 in 20 seems like a good number for type 1 error probability. And Homo sapiens love their rules, so it stuck. So if this PowerPoint by Pearson is allowed to have so much repetition, then my narration can have a little repetition also. Yeah. All right, so next example. Cell phone use while driving impair reaction times. This is one of these experiments that seem like common sense and almost moronic to study. Like, really? Who thinks they can drive while using a cell phone? Like, do you really have to study this? But someone might have gotten a grant to study this, you know? An experiment investigated whether cell phone use impairs drivers' reaction times, using a sample of students from the University of Utah. Ooh, actually, I'm interested now. So we got 64 college students. 32 were randomly assigned to cell phone group, 32 to the control group. And you put them in a car? Okay. All right, let's see. You know, I'm taking this as it comes. All right. Okay, students used a machine that simulated driving. Okay, they're playing a video game. Okay, so if I was critiquing this, you know, first of all, I'd be like, really? A simulation? I mean, like, you're not going to put them in an actual car with cones and, college students, yeah. Okay. At irregular periods, a target flashed red or green. You know, this is like real driving. Now, this is the concept of generalizability or external validity. If you're a psychology major, you will be using the term external validity. And if you are majoring in STEM, STEM fields, science, technology, engineering, and mathematics, you'll more likely be using the term generalizability. If I had to critique this, the first thing that comes to my mind is, really? This is how you're, okay, so, right away, I'm not really seeing great external validity with this, but whatever, So participants were instructed to press a brake button. Okay, come on. When you drive, it's not a button, it's a pedal. As soon as possible when they detected a red light. Yeah, this has generalizability, right? The control group listened to radio or books on tape while they performed the simulated driving. The cell phone group carried out a conversation about a political issue with someone in a separate room. Now, it doesn't say whether they were doing it hands-free or not. So, I have cell phone conversations with people all the time, but hands-free. It's in a little holder, and that's the way we're supposed to do it, hands-free. Just like you could have a conversation with someone next to you when you're driving, but I never look at the cell phone while I'm driving, All right. For each subject, the experiment analyzed their mean response time over all the trials. Averaged over all the trials and subjects, the mean response time for the cell phone group was 585.2 milliseconds. That's a pretty long response time. 585.2 milliseconds, that seems pretty long. Just for your own edification, a millisecond is a thousandth of a second. It's not a millionth of a second. So people make that mistake. A millisecond is a thousandth of a second, which means there are 1,000 milliseconds in 1 second. And it's very important to know this in the field of audio engineering because you often have to calculate release times for your compressor if you're an audio engineer, and you need to know this. So the mean response time for the control group was 533.7 milliseconds, a shorter response time, right? Quicker, shorter, quicker, right? This is longer, which is worse. This is shorter, which is better. You want your response to the stimulus to be as quick as possible. Okay. Oh, this is a full slide here. Let's read the text first and then I'll go through all this stuff. So the app shows the difference in the means, the standard error, the T statistic. Now, it's missing the letter D. It should say and the resulting p-value. So Pearson's quality control missed this one. It should say and the resulting p-value, which is also illustrated in the graph for the T distribution. Question: does either box plot show any features that could affect the analysis? This is a very good question. So let's look at this box plot. Now, let's review a little bit, right? Nothing wrong with the review. Do you remember what this horizontal bar represents? A, the mean. B, the median. C, the mode. D, the standard deviation. E, none of the above. And the answer is dun, 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 the median. The median, the middle number. So do you see how there's more mass above the median than there is below? Here there's skewness. Here this median, maybe there's a little more mass above, but not a lot. So it looks like there's some skewness here. And remember, the normal distribution is symmetric. There is no skewness in the normal distribution. So seeing this makes me want to do something. So let me ask you, I'm trying to make this as interactive as possible. When I see this skewness, what do you think it makes me want to do? Time to think. Let's fire up SAS. What test do you think I'm going to want to run? The Shapiro-Wilk test for normality. I'm going to want to see if the cell phone group, I'm going to do it for both because it's just, a couple of lines of code and you just get it. Oh, and here, remember from Stats 1 when you see this little thing all the way out here, right past the fences of the box? See, this is outside the fences, right? Outside the fences of the box plot. What is this thing called? Do you remember from Stats 1? It's called an outlier. So not only do you have skewness, but you got an outlier. Now, the outlier could be a data entry error, You always got to test your outliers because they could be data entry errors. but you never want to throw them in the garbage based on some criteria that doesn't make sense. So just because you have an outlier doesn't mean it's garbage. You don't throw it in the garbage. If it's a data entry error, you throw it in the garbage. But one of my mentors when I was learning statistics at the Stony Brook University, an amazing statistician who focused on reliability theory, Lawrence Baxter, he told us, he said, your outliers sometimes are the most important observations in your data sets. You don't throw them in the garbage unless they're data entry errors, though I don't think he used the word garbage, right? That's more my way of speaking. So we got skewness, we got an outlier that tells us I'd use the Shapiro-Wilk test if I'm going to use the t-test, and I'm not going to hang my hat on robustness unless I really know that, you have independent random samples. But anyway, let's cut to the chase here. Let's go right to the p-value. You see we have a p-value of 1%, 0.011. You take this little decimal point here, and you go doot, doot. You got 1.1%, a p-value of 1.1%. And on planet Earth, because R.A. Fisher glibly, and I don't think he expected the world to just follow the 5% significance level. That's why I can't put myself in his mind, but I'm pretty sure the reason why he said it so glibly was so that people wouldn't just arbitrarily, follow the rules. But on planet Earth, the de facto significance level is 5%. And so here we have a p-value of 1.1%, which is less than or equal to 5%. This tells us, assuming the distributional assumptions are satisfied, the appropriate decision. No, he didn't say the correct decision. Never say the correct decision. Human beings don't know if we're making the correct decision. We make an appropriate decision based on the numbers we crunch. The appropriate decision is to reject the null hypothesis because we have a tiny little p-value. But I'd still run the Wilcoxon rank sum test. I'd still run the rank sum test and just make sure we, it comports with this. Or I'd run, the Shapiro-Wilk test. And if you get a nice high p-value for the Shapiro-Wilk test and you get a nice low p-value for this test, well, now I would be comfortable saying, yeah, there's definitely a statistically significant difference at the 5% significance level. Sure. Yeah, absolutely. All right, so this is repetition. The null hypothesis is that there's no difference. The alternative hypothesis is that there is a difference. A difference in what? Response time. Response time in what units? Milliseconds. What's a millisecond? Not a millionth of a second, but 1,000th of a second. So this is repetition. We got the p-value of 1.1%. Oh, now we have a nice little picture. This is really good. So if we have the p-value of 1.1%, and it's a two-tailed p-value, we have these two tails over here. We have a little tiny bit of probability density here, and we have a tiny little bit of the same amount, that same tiny little bit of probability density over here. And this probability density, which is the area under this probability density function, and this probability density, which is the area under this probability density function over here, it adds up to 1.1%, which is a statistically significant p-value. at the 5% significance level. So the p-value is less than the default significance level on planet Earth, which is 5%. So we reject the null hypothesis. In other words, there is sufficient evidence to conclude that the population mean response times in milliseconds differ between cell phone and control groups. The sample means suggest that the population mean is higher for the cell phone group. What do the box plots tell us? Oh, maybe I should have waited for that. Yeah, I spilled the beans on this one. I did. What do the box plots tell us? There's an extreme outlier for the cell phone group. We already discussed that. It's a good idea to make sure the results of the analysis aren't affected too strongly by that single observation. Yeah, that's true. That's called an influence analysis. An influence analysis, but again, you don't throw it in the garbage unless there's a reason to throw it in the garbage, right? And it could be a data entry. So very, very often you have data entry errors. That's so common because a lot of companies don't want to spend the money to have the data entered twice or three times and then compared in what's called a data adjudication process. A data adjudication process. So data should usually be entered 2 or 3 times. The data sets are compared. And SAS has a procedure to do that called proc compare. So in the real world, that's how you do it. So you can delete the extreme outlier and redo the analysis. That's called an influence analysis. But then what happens if you get radically different results? Now you have to go and really, if you're a halfway decent statistician and you're ethical and you actually care, you have to investigate. You have to talk to the people who collected the data. You have to say, hey, man, I found an outlier. What are we going to do about this? You have to, They don't always like when you do that, though. Unless it helps their narrative, who's paying your salary. Then they'll love you for it. So the mean and standard deviation for the cell phone group now decreases substantially. However, the T statistic is not much different. The p-value isn't much different. So what do we conclude? It doesn't even matter whether we throw it in the garbage. But you shouldn't throw it in the garbage unless you have a reason to throw it in the garbage. But it's a good influence analysis. He looked at it. It's easy. Take the outlier out, run it again. It's not like you're doing it by hand. In the old days, you had to do this by hand, All right. So in practice, thank God. I'm so glad he actually put that in. Okay, good. So in practice, you should not delete outliers from a data set without sufficient cause. So that is, if it seems like the observation was incorrectly recorded, a data entry error. It is, however, a good idea to check for sensitivity of an analysis to an outlier. Okay, that's called an influence analysis. If the results change much, it means that the inference, including the outlier, is on shaky ground, which means the statistician needs to have some conversations. You got to be able to have some conversations. You do. They may not like you for it, but you have to. Oh, this is great. See, this is why Alan, okay, so there's a good chance that Alan, okay, this is great. Comparing two groups with bootstrap or permutation resampling. This is modern. This is modern statistical practice. This is great. Thank you, Alan Agresti.